Yeah, good morning.
Good morning, sir.
Yeah, let's resume our discussion. Any quick points on the last class before I move on to the current discussion of today's class? What did we discuss in the last class? Quickly, a couple of points from your side.
So, sir, we started off with some scale invariant feature transformation, our discussion of where to look and what to look in an image while segmenting and joining. Then we were discussing about various panoramic data and all that. Then we talked about video processing, how we can use to detect motion in the image and optical vector flows. So the same motion we can take to cyclones and other cloud tracking. Then we talk about visual processing, right? And then we came to depth and disparity estimation. Then we were discussing various applications of computer vision where it can be used. And we were talking about data, how formation of data in deep learning is extremely important. So then we discussed that deep learning is about classification, detection, segmentation, and then retrieval of information from the data. So yeah.
Yeah, good. So what about others?
I think we also discuss the general flow. Like first we do some kind of pre-processing, then we extract some features, and then based on those features we do classification on that.
Fine. So what else on the similar lines? What else did we discuss?
We have discussed about getting panoramic views, like stitching of two images, and mainly based on pixels that are having high contrast. That was the main thing we have searched for while doing that.
Okay, fine. Okay, so for deep learning, we have mentioned that it has the ability to extract features and do classification together as well through effective learning. So, and in fact, it can do to some extent reprocessing, feature extraction, classification together with learning. Okay, that's also we have mentioned. Fine. So let's now move towards bringing some mathematical basics to our discussion. See, what did we discuss? If we have an image, okay, and if you want to find a particular template in the image, okay, so this is assume that this template, and this is the image. See, let it be a classification problem where we want to classify one template versus other test samples to one of the category, okay, or let it be a object detection problem where we want to detect where the particular template is, okay, or we would like to have a tracking problem where we have a sequence of images and we would like to identify the location of the object in all sequence of frames, in each of the frames in the sequence, okay, or we would like to have a 3D reconstruction problem where given left and right images, we would like to find out the relative shift of a template patch here. Okay, that means each patch becomes a template patch now. And with respect to the right image. Okay, so how much shift has it has undergone? Okay, or let it be an optical flow problem. So in each of these things, what is common if you see, one very essential thing that's common is what? So can some of you tell instead of me telling the common things? Quickly, some inputs are welcome. For all these CV tasks, one thing that is common is what? Feature extraction. See, when I want to make any template matching or whatever, what do? I can't match at the pixel level. I don't match usually at the pixel level. The reason being, the pixel levels information is not agnostic to, or it's not robust to variations in intensity, that is photometric variations and geometric variations. It may be some slightly like it doesn't capture the shape information as such. It may more tend to give the intensity information, which may not be very apt for template matching. Okay, especially the content of the image will not be completely looked at by the intensity information. So for that reason, we usually make the feature extraction. The other thing that is common is we would like to find out the similarity. Okay, we would like to find out the similarity between the patches. So how do we quantify the similarity is also of great importance. Okay, and then after that, once we find the similarity, we may find the appropriate match, okay, in terms of our correspondence in many problems, and that will essentially establish the inference that we would like to bring in. Okay, so now the question is, how do we find out the similarity? So as you know, there are some measures like correlation for finding similarity, and there are some measures like Euclidean distance to find out the dissimilarity, which can also be used for inferring the similarity. Okay, so now what I will just give you a typical scenario. Let X be the image patch. Okay, and then W be in some sense a learning matrix that will help us to learn the features, okay, from X. Somehow for time being, you assume that W will help us. W can be either a matrix or it can be a vector. In some cases, what may happen is W is simply a vector, okay, and of same dimension as X. That will also help us to extract a particular features from X. Okay, and then the if it is a vector, this is also a vector. If this is D cross 1 vector, X is D cross 1 vector, X1 to XD. Okay, and then W is also now D cross 1 vector, W1 to WD. Okay, in such case, Y is a scalar. What does Y gives? What do you think Y gives now? Can some of you tell, given this context, what the Y may give?
Similarity.
A scalar.
Yeah, sure, it's a scalar. What scalar? What its value signifies?
The similarity between the patches.
Okay, this W, when I learn appropriately, captures the features of the template. Okay, and then X is what? X is a test patch, features of the test patch. Okay, does Y captures what now?
Similarity between the features of our template and test patch.
Right. So if Y is high means what? Y is high means
The features match.
they match. Okay, if Y is not very high means they doesn't match. Okay, this is a kind of, this is a matching score for W template versus the patch. So what usually we would like to do is, say, assume that in some of the scenarios, I may use, in addition to this Y, I may use some nonlinear function to scale this W transpose X, which is in real scale to 0 and 1. In that case, what happens? This F is a function which will scale this score. Okay, so I may just give a slightly different symbol for it, but yeah, I just, you assume that this is the other way of writing. That means this is one possibility, okay, of arriving at the scores, comparing the template features and the test sample features, test image patch features. Test sample for us is image patch or in image itself sometimes. Okay, and the other thing is W transpose X, which is scale. This is in some sense a scaling function. Okay, so it can be, it scales W transpose X to 0 to 1 range. In that case, what do you think Y gives? What do you, if it scales between 0 to 1, how can I interpret this Y as? Can one of you comment on that? So if I write this as Q, okay, what can I comment, Q or Y? What can I comment, like what the value? Yes, the Y gives the probability, or the Q gives the probability with which the template and the test sample matches. Okay, so now I can use this analogy either to find out the probability of match or to find out the score of the match. Hope both are clear to you. Okay, so just if you wish me to be explicitly different, we can write this as yes. Okay, and then our small s here, and we can write this as y. Okay, just to distinguish. Okay, so now the next question is, see, usually in a classification problem, assume that we have two class classification problem. Just assume that template is a foreground object, that is face. Assume that it is a foreground object, and the background is the other patches where there is no face. Okay, so the classification now I would like to do between face and non-face. Okay, so here the y equal to 1 here, y equal to 0 here. This is how I would like to train a model or a classifier. Okay, so if I train like that, what essentially happens? The W is the one which will capture the template feature relation. See, template feature, in this case, you are saying a single template feature. What may happen in real situations? I don't want to bias my all classification and other things with a single template feature. Okay, template, single template. I may have hundreds of representations or tens and thousands of representations or thousands of representations for the template. I would like to have a represented, this W has to be representative of all these things. Okay, sometimes it can happen, sometimes it may not be sufficient to have capture in a single representation. But assume that just to have a simplified case, I would like to capture this W as capturing the whole variations of that class. Okay, if I am classifying as face, non-face, this W has to capture the variations of all face, and it has to give a W transpose X has to very high score, or f of W transpose X has to be 1 for a face. Okay, when X is a face. When X is not face, I would like to have this as 0. So that's actually, this is exactly the binary classification problem. Okay, so here is what we are essentially modeling the binary classification problem in a simple sense. This is also posing a classification problem or a similarity assessment problem. So now in such cases, what is important is to formulate a quantification function or a cost function. What should this cost function do? What should this cost function do? See, if I assume that I have now samples, x1, x2, and so on. So I'm writing x1, x2, and xn, for example. These are all the samples or the patches. Some corresponds to face images, and some corresponds to non-face images. Now, if I effectively train a classifier, or if I capture W, if the W has to be such that to classify all samples to their appropriate classes, then what has to happen? Any guess on that? Has to be Y minus W transpose X. Has to be what? Has to be minimum, right? Because Y, essentially what we said, Y gives the labels. Labels means for all the class samples belonging to face class, it is 1. For all the samples belonging to non-face class, it is 0. That's how this Y is. Okay. So now given this context, in that case, what has to happen? We minimize effectively the discrepancy between the label, true label Y, and this is essentially the predicted probability or the predicted label Y hat. Okay. So this you can also consider it as the true probability or label, and this is the predicted probability or estimated or label. Okay, so here you can see that Y hat may range between 0 to 1. Okay, 0.8 may come, 0.2 may come, and so on, because it's essentially a real value between 0 and 1. It gives how much close we are to the positive class or to the negative class. Okay, that's what it infers. So essentially what we require in understanding, like what are the basic mathematics required for it are to deal with the matrices and vectors, essentially, that is formulating the the similarity functions using vectors, matrices, and so on, and then formulating the cost functions, finding out the match between the true label and the predicted label, or the true scores and the predicted scores. So in this case, what has to happen? So S minus, see if I have these class scores, so I assume that if it is positive class, I have to have a higher score. Okay. So if I roughly know the class scores, I may say that S minus W transpose X has to be minimum again. I may say that for positive class, this score has to be very high, maybe whatever. Okay. Some 100 or whatever. And negative class, it is low. So in essentially instead of this, what we can do is in maximizing W transpose X itself. Okay, this may be our problem if it belongs to positive class. Okay, so we will see how exactly we formulate the cost functions. But the idea now we have to get is we have to deal with the matrices and vectors, and we also have to formulate the cost functions, and we also need to deal with minimization or maximization problems, a little bit of optimization problems. Within these optimization problems, you may have matrices, vectors, okay, and scalars and so on, all the aspects. Okay, so here just to give you a example where you need the matrices. So assume that rather than classifying to 2 classes, I would like to classify to 5 classes. Okay, so in that case, what may happen? See, this feature X may belongs to any of the 5 classes, and I would like to capture in score. Okay, score vector again, score of all 5 classes. That means X belonging to first class, X belonging to second class, and so on. And the respective scores has to be there in S. So in that case, if this is D cross 1 and this is 5 cross 1, because I have to have class scores of class 1, class 2, and class 5, and this will be 5 cross D. So in such cases, W is a matrix. Even usual procedure is scores are ranging from minus infinity, like 0 to infinity, or minus infinity to infinity, based on how the X and W are. Okay. But however, the probabilities, if we convert or if we bring into the 0 to 1 scale, it is easier for us to assess or compare. The scores are the class labels. Okay. So for that reason, for most of the applications, we will bring after this, okay, in some sense, okay, whatever may be the function f here, we may bring it to the range, in the range probably 0 to 1 or minus 1 to 1 and so on. Okay, so that we have a definite range for comparison. And in this case, this y also can be a vector. Please note that. This f can be a vector function as well. Okay, that means, say, see if this w, this whole thing, as we said, 5 cross 1 vector, and this f will bring the first element to the first element this side, second element to the second element this side, and so on through whatever nonlinear operation we perform. Okay, so and then y also becomes now 5 cross 1 vector, providing the class scores or the class probabilities of the class 1, class 2, and up to class 5. Is this clear? Up to here, are the things clear? Okay, I assume it is fine. So now let's bring in little bit of the math that is required. See, first of all, before going to the optimization function, that is finding out the minima and maxima and so on. Okay, so if you would like to define similarity between two vectors, how do we define? Just quickly tell the similarity and dissimilarity measures. Okay, between x and y. When x and y are vectors, how do we define similarity? How do you define? Okay, correlation is a measure that gives similarity. And more than that, if we would like to confine the similarity also computed in a particular range, we can use normalized cross correlation. X transpose Y by. See, this is fine with the vectors. How do you think we define with the matrices? If X and Y are matrices, okay, this is essentially element-wise product, okay, of all the elements of X to the Y, okay, and then sum them. This is in some sense the measure of similarity between the matrices. Here, norm X is nothing but a matrix norm, and norm Y is nothing but a matrix norm again here. Okay, that's essentially norm X is defined as okay, and under square root. Hope you know this. So you can easily extend the definition from one like vectors to matrices. Okay, so now if you would like to find out dissimilarity, this similarity can be measured through correlation or normalized cross correlation. Of course, there are few other methods. So this normalized cross correlation can also be okay sometimes related with the angle between the vectors. Okay, and then theta, you can measure the angle between the vectors also as a measure of similarity. Okay, and then if we would like to measure dissimilarity, how do you measure dissimilarity? One measure is by Euclidean distance, norm of x minus y whole square. So one way of measuring dissimilarity is through Euclidean distance. Does anybody know any other ways of measuring dissimilarity? So we will define later. We can also use the probabilities to define, like measure the dissimilarity, that is through KL divergence. Okay, we will define that in more better way. So this measures if we have two like probability density functions, what is the deviation of one probability density function from the other probability density function. That means how similar a particular probability density function to other. So, or to move towards other probability density function, what is the distance that's lying between them? Okay, so that essentially is being measured by KL divergence. Hope you also know about Moharana-based distance. Essentially, when we have X and Y both being random variables, you can also measure their distance or how a particular random variable varies from the other random variable through Moharana-based distance. That is when you have actually the features modeled as random vectors, you can also measure their distance using Moharana-based distance. That sigma here denotes the covariance. Okay, we will see that little later. Okay, so these are some measures of similarity and dissimilarity. Now, given that actually let's start with simple similarity measure. And then we have S equal to some double transpose X, simple function. Here, what we may need to do is, as I mentioned, we may need to formulate the cos function, and we would like to do minimization of the cos function. Say if I formulate a cos function, the cos function J is the discrepancy between y minus f of double transpose x. Okay. And if I would like to minimize this j with respect to w, why I would like to minimize j with respect to w? Because x is given, which is test sample, y are given, which are labels. These are test samples and these are labels. What I want to learn in the algorithm is essentially the w. This w has to capture the relation between the input samples of different classes and their corresponding labels. Okay, you can consider it as a mapping also. Okay, f is a mapping function and w plays a role of parameters of mapping, okay, or learning to determine through learning that will map the input samples x to the labels y. I hope this is clear. In such cases, what we may need to do is we would like to find out we would like to minimize j with respect to w. And this, if we would like to minimize, what essentially we do? What is the procedure of minimization?
Gradient.
So what? Yeah, gradient with respect to what? Dou j by dou w I will find. And then I will equate to 0 to find out the effective solution for w. This is one procedure of minimization. There are other procedures of minimization that I will discuss shortly now. One is one well-known way, other than directly equating the differential to 0, is to iteratively arrive at to the solution of w. The reason being, in some cases, especially when this is a linear function, you differential equating to 0 doesn't yield a solution for w. It just gives a like the w itself will disappear if you try to equate to 0 and do something. Okay, so in such case, what is the feasible way to do is you can find out dou j by dou w, that is gradient, and then update the w in an iterative way such that we move towards the optimal solution or the w that minimizes j. Okay, so that's that is one optimization procedure for doing that is referred as gradient descent. Okay, so what we do here is, if we have a function and if you would like to move towards a minima, then what we do, if we are here at this location, what we do is we find out the direction of gradient and then move in the direction opposite to the direction of gradient. See, gradient is like this, means gradient is denoted by tangent of the curve. Okay, so assume that, just to simplify the discussion here, if this is f of x or f of w is equal to w minus 2 whole square. Okay, and if we would like to find out the w that minimizes this f of w, then what we do is we may start with, say, w equal to 0. Initially, we may start with w naught is equal to 0. Now, what I do, I will find out dou f by dou w. That is the slope of the curve at given w. Okay, slope of the curve dou f by dou w, if you see here, for this is what? Dou f by dou w is 2 into w minus 2. Okay, so here this slope I would like to see in which direction it is, positive or negative. Now w equal to 0, if I substitute, dou f by dou w equal to minus 4 at w equal to 0. Right? So it is in negative direction. Or whenever the like the tangent is downwards, it is negative direction. Whenever the tangent is upwards, it is positive direction. That's how the slope is defined. Okay. So now, since the slope is negative, what I do, or the gradient is negative, I will move in the forward direction. How much should I move? I can decide based on the how fast I would like to move to the minima. Okay, or how stable I can study, I can move to the minima. So if I move by some say some eta times, what then the update equation for w to arrive at a next closer value of W that is closer to the minima, next value of W that is closer to the minima is given by this in gradient descent. Wt plus 1 equal to Wt minus eta times dou F by dou W. Okay. So as you can see here, this now if we just apply the gradient descent here, okay, then where do we move? Wt plus 1 is equal to, where were we before? Assume that eta equal to 1 by 2. Okay. Now 0 minus half into minus 4, right? So which is equal to 2. So now did we reach to the minima or not? Yes. Yeah, here actually W equal to 0 and then W equal to 2 here. Okay, this is the minima of the curve, right? So you are able to reach to the minima like this. So if eta, in case if eta equal to 1 by 4, we may not reach to the minima. In that case, what will happen? Wt plus 1 is equal to 0 minus of minus 1 by 4 and so on minus 1. Okay, which is minus 1. In that case, what do? We perform one more iteration of gradient descent. So again, dou F by dou W, at W equal to minus 1, sorry, W equal to minus of minus 1, right? That is plus 1. If we see, then what is it? What is the value of dou F by dou W? You can substitute here, right? So 2 into minus 1, which is equal to minus 2. So essentially, again, now you can apply gradient descent. Previously, we were at 1 minus 1 by 4 minus 2, which is equal to 1.5. Okay, so you have moved towards. So previously, you moved up to here in first iteration. In second iteration, you are up to here. Third iteration, you may move here and so on. Then you will come closer to the minima, right? So this is referred to as gradient descent. This is the optimization procedure that helps us to move progressively towards the minima when we have an optimization function like this, or when we have some kind of minimization problem like this. Of course, we can also apply similar techniques for maximization. That's referred to as gradient ascent. Okay, so where we may have a maximization problem. If we would like to bring in, if we would like to reach to the maxima, then we can reach out using gradient ascent. What do you think in gradient ascent we will do? Any guess on that?
We move towards the maximum gradient.
Yeah, that's fine. How should be the update equation?
We'll remove the minus sign with plus sign, replace.
Yeah, that's all. Okay. So here simply Wt plus eta times dou F by dou W. That means what does it indicate? In gradient ascent, okay, if we have a problem like this, we are moving towards the maximum value here. Okay. So what essentially we are doing? We are moving in the direction of gradient now. Okay, previously we are moving opposite to the direction of gradient. Now we are moving in the direction of gradient. Okay, so here moving opposite to the direction of gradient. Okay, fine. So now this roughly, these are the kind of optimizations we use. Now, even to do all this, we need to do differentiation. Okay. So now just to start our differentiation knowledge, or the vector calculus knowledge to develop. So let's try to find out dou S by dou W. See, we may encounter this kind of problems while doing, since this is anyway W transpose X, somewhere I would like to differentiate with respect to the vector W, not just a scalar W. Okay, so here all examples that we have given are with scalars. Okay, but I may need to do sometimes with vectors. Sometimes I may need to do even with matrices. Okay, so for that reason, let's try to understand and right now dou S by dou W. Can one of you guess what will be dou S by dou W is? We should define it first. So how do we define it? See, S here is a scalar. Please note that. So dou S by dou W1, dou S by dou W D. This is how we define dou S by dou W, a vector derivative in terms of scalar derivatives. Is this clear? So essentially, in fact, you need not put even S here. So better definition is dou S by dou W, dou by dou W itself, where W is a vector, is dou by dou W1 and dou by dou W D. If we have D dimensions for W, what essentially we are doing is we are finding out the rate of change with respect to the each direction. Okay, and then we are just indicating in the vector W the rate of change with respect to W1, W2 and W. That's all. Okay. So here please note that X is D cross 1 vector and W is also D cross 1 vector. Okay. So hope this is clear. This just carry forward from previous discussion. So now I would like to explicitly find out dou S by dou W in this case when S equal to, or S here is equal to W transpose X. Okay. So if you would like to have an intermediate step, S is equal to what? W1 X1 plus W2 X2 plus and so on WD XD. Is this fine?
Yes, sir.
Right. So now dou S by dou W is nothing but, how do I write it? Dou S by dou W1, dou S by dou W D. Okay, what is dou S by dou W1 now? Even this
X1,
X1. Okay, and then dou S by dou W2, it will be here.
X2,
Yeah. And then X2 and so on up to dou S by dou WD
XD.
is XD. That's all. So dou S by dou W is nothing but vector X. Hope this is clear. Right? Okay. So now the next question is, so assume that we would like to find out now, instead of writing S W transpose X, okay, somebody has written in some function S as X transpose W. Okay, it can happen, right? So now again I would like to find dou S by dou W. Okay, in this case, what do you think is the solution?
It will be X only.
It will be X only? Yes, it will be X only because the definition doesn't change. Okay, dou S by dou W is nothing but dou W dou S1, dou S by dou W D. Okay, whether we write this side or that side, this solution is, say this expansion is same. That is W1 X1 or X1 W1, X1 W1 plus X2 W2 plus and so on XD WD. Right? And hence this is X1 and XD. Right? And hence this is equal to X. Correct? Is this correct or not? See, in some other problem, somebody might have written S equal to X transpose X. Okay, somehow it happened. Okay, or W transpose W instead of X transpose X, since we are finding derivative with respect to W. Okay, W transpose W, okay, minus W transpose X or something might be there, other terms. Okay, just now we are particularly interested in finding the derivative with respect to W when S is W transpose W. Just this is for analytical aspect. What do you think is the answer? S is W transpose W. Okay, and then we want to find dou S by dou W. Any answer on this?
2 times W.
2 times W1,
Okay.
2 W2 till 2 WD.
Okay, so 2 times W1, W2. Okay, so essentially, if those who want to do procedure through procedure, you can write this as W1 square plus W2 square and so on up to WD square. Okay, and then differentiate 2W1, 2W2 and so on 2WD. Okay, and then this essentially is nothing but 2 times W. Okay, please note that all is D cross 1. See, if I differentiate a vector with respect to a vector, please note that dou S by dou W, when this is W is D cross 1, dou by dou W is also D cross 1. Okay, please make a note of it. Okay, this implies this. Okay, fine. So now let's move on to the discussion when we have matrices. Okay, assume that now I have vector S, which is matrix X, W into X. Okay. Because as I mentioned in some of the problems, this is also quite common to get. Oh, it may be multi-class classification problem. Okay. So now what I want to do, dou S by dou W I want to define. That's fine. That's a bigger thing. At least I would like to define dou S by dou X. Okay. I would like to use this as intermediate value for something. Okay. So here, yes, X is a vector and S is a vector. See, I may formulate in different ways. Okay, X itself may be sometimes matrix. That means several features or several templates I may bring in. And WBA just a learning parameter for mapping something. Okay, this is also common. This is D cross 1 and this can be say whatever D cross D or whatever. And this may be D cross D. Okay, and then this is D cross 1 and then this is C cross. C is the number of classes C cross D. And this C cross D. Okay, so different scenarios will occur later. Okay, we will see that. In fact, we will also discuss some other scenario where actually S can be obtained as X transpose W into X. Okay, W is a matrix. This is D cross 1 and this is D cross D in between. Okay, and then this is 1 cross D. And the whole thing is 1 cross 1. Okay, so these different scenarios usually occur. Okay, in when we model the deep neural networks, so we should be familiar how to do the how to write the gradients first. Okay, and then use the in a bigger optimization problem, these gradients will be smaller part of it, because as you have seen here, if you would like to perform a bigger optimization, there will be somewhere the gradients involved. Okay, so now the question is, so dou S by dou W, we will bother later because S is a vector. Okay, this is vector differentiated with respect to matrix. So this will be, in fact, the dimensions will be even more. It's a tensor. This is referred to as. Tensor means you can't represent in as a matrix. Okay, a set of matrices. It's a tensor. 3 dimension will bring in. This dou S by dou X is what? Vector differentiated with respect to another vector. Okay, even in this case, if you try to write dou S by dou W. Okay, this is again vector differentiated by vector. Okay, so here if you would like to write these things, so just for our simplicity or ease of understanding, I will write this as S equal to M into W. Okay, this M can be from X. Okay, from set of X case. Okay, but just for having a notational convenience, M as a matrix, because X we are familiar with being a vector. So I have written this as matrix. Okay, so now what I want to do is dou S by dou W I want to define. This is D cross 1 and this is N cross D, let it be. And this is the N cross, so 1. Okay, this can be N cross D or whatever, what dimension it may be. Dou S by dou W I want to write. Okay. So these are all the several possibilities. In that, now what we are discussing is a derivation of vector versus vector. Okay. So now we have to define this first, right? Since S is a vector, S1 up to Sn it may be. Okay. And then W is a vector. It may have W1 up to W. Okay. So this is the dimensions given. So I have to define here these derivatives have to be found for each component of S with respect to each component of W, right? So it will become a matrix. Okay. Since we have already defined dou by dou W for a single S1, let's stick to that. So dou S1, if we have only one component in S, then exactly we could have done in the same way. Dou S by dou W1 and dou S1 by dou WD. Okay, we could have done exactly in the same way. If we now have the second component of S, that is when we write S as a matrix multiplied by W, you will have actually second component dou S2 by dou W1. Again, we need to see partial derivative or derivative with respect to each component of W. So we write this as dou SD by dou WD, dou S2 by dou WD. We do the same for all components of S, dou Sn by dou W1 to dou Sn by dou WD. This is how we define the derivative of a vector with respect to another vector. Is this clear?
Yes, sir.
Yes. So if this is clear, the next question is, in this case, what is this dou S by dou W? Please note that S1 to Sn if I write, using this, let Mij, okay, be the matrix elements. I equal to say 1 to n and then j equal to 1 to d. Okay, matrix elements of M. Okay, so in that case, how do I write this? M11, M1d, Mn1. Okay, I'm writing small letters for these values, internal values. You can choose to write either small or capitals. Mnd. Okay, and then here W1 to WD. Okay, so now I can write S1 equal to M11 W1 plus M12 W2 plus M13 W3 plus and so on M1D WD, right? So now I can compute dou S1 by dou W1. Yes or no? And similarly dou S2 by dou W1. Each of them I can compute. Given this definition, now what is the solution?
M transpose.
Okay, M transpose, very good. Okay, so any other answers? Yeah, this is W. So if we write now, dou S by dou W1 is nothing but what? M11. Dou S2 by dou W1. Dou S2 is here. Okay, dou W1. If we bring in M21 will come here, right? Because M21 W1 plus and so on it will come, right? Similarly here, dou Sn by W1, that is Mn1, right? Now similarly if I start writing, okay, dou S1 by dou W2, that is M12 and so on. Here it is dou Sn by W2, dou Sn by W2, that is dou Mn2 and so on, dou M
1D.
Yeah, 1D, very good. And Mnd. So this is nothing but, is this M or M transpose? Correct?
Yes, sir.
Yes. So essentially now the matrix like vector to vector derivative results in matrix, and then when S equal to M into W, dou S by dou W is M transpose. Okay, this is very like easy to derive and easy to remember as well. Okay, so in some cases actually what may happen is we will see that. So we may have several of layers. At each layer you may result in such solution. Okay, and you need to use them, but the same thing will repeat several times. Okay, that's the advantage. So let's conclude here. Just say when we have S equal to W transpose M into W, there as well you try to find dou S by dou W. Okay, so let's conclude now in this this class here. Thank you.